Lesson one of this module chapter, we are going to be going over an overview of the oceans. So, oceanographers, that's people that study the ocean, use all kinds of different tools to study the ocean. They use thermometers, sonar, floats. They use submersibles like submarines. They use computers, all kinds of different devices to study the oceans. And a side scan sonar is one device that sends sound down sideways to map like the mountain sides and see where they are and where they end. Satellites are used to measure temperature and currents and wavelengths. Scientists use floats, things that are different types of floats that float out in the ocean to measure water temperature, salinity, how many gases are there, and the nutrients in the water. You will actually do a lab where you will look at this and see different actual monitoring systems that the US government has and look at that. So, all of these are different ways of studying the ocean. And this is a great timeline in oceanography and developments. It's basically a very unstudied frontier for how much of our Earth it takes up. Scientists estimate that the ocean is approximately 4.56 billion years old. So it was formed shortly after the Earth was formed. Um, and so we know that oceans have been around because we know the age of certain rocks. Those can be dated. And lava gets very glassy when it cools quickly in the water. So if they can date the rocks to be a certain age and then see that it's very glassy, like it came in contact with water, there's a very good chance that there was water there. So where did this water come from? Remote sources, remote off of the earth, meaning things that came and hit the earth. You could have comets, you could have meteorites, and then some of that water, when water was brought here, some of the water had to come up from deep inside of the earth, and this actually happens during volcanic eruptions. So volcanic eruptions bring up things other than lava, including water vapor, carbon dioxide. And so water from deep inside of the earth can come to the top because of volcanic eruptions. So I'm going through this kind of quickly because this is a long section and I don't want to be on video for way too long where you don't want to pay attention. Um, so we have a very blue planet. Our planet is very blue, and 81% of our southern hemisphere is water. It's water. And then 61% of the northern hemisphere is water, and 71% of our total planet is covered in water. So you can see when they turn the earth like this, um, more land, but still 61% water. And when you look at the earth from this direction, 81% water. It's an interesting view to look at it that way. So, global sea level is the level of the ocean surface, and it's fallen, risen and fallen by hundreds of meters at different points in our Earth's history. So, rising sea level can cause flooding, it can cause habitat loss. So, it's something to watch. Something that's interesting is that as the ocean water gets warmer, warm water actually expands. So, it will actually expand a little bit. Just like if you were boiling water, it just kind of it will expand a little bit. And so warmer waters also take up a little more space than colder waters. So there's various oceans and it goes over the major oceans. You can look at those and learn that. That's not something that's new to you. Something that is interesting here is about 50% of the oxygen in the atmosphere comes from phytoplankton. That's plant plankton in the ocean. And then something that's often overlooked is that our oceans are a major, what's called a sink, or your book calls them a reservoir of carbon dioxide. So it gets rid of a lot of carbon dioxide for us that will actually move and sink to the bottom of the ocean. So they're also a source of heat and moisture, which they keep us warm and insulate us, and they also provide us rain. When that air passes over it, it collects a lot of water that is precipitation for us later. So, what is in seawater? The chemical makeup or composition of seawater is not exactly the same everywhere. If you measure different aspects of seawater, it's not going to have the same composition everywhere you go. And three things that affect the chemical composition of seawater are wave action, vertical movements of water, and biological activity. So there's more oxygen, or there tends to be, at the surface of the water because of photosynthesis. There also tends to be a lot of silicates, silica at the bottom of the ocean from things that have died and their shells have collected. Now, near the surface, a lot of those living things, there's less silicates because they pull them out to make their shells. And then there's a lot more at the bottom. Um, then saltier water, the colder water is, the more salt that it can carry. So cold water carries a lot more salt than warm water. And in our very cold Pacific Ocean, in our very cold Pacific Ocean, um, we tend to carry a lot of salt, and because our water tends to be very cold. So there's different sources of salt, a lot of which is from the land. And salt is somewhat removed from the oceans by evaporation. You can have salt collecting, you can have wind blow it off of the oceans, and some is taken out by humans and sometimes even by other organisms that accumulated in their bodies. They die and then it stays in their bodies at the bottom of the ocean, but not in the water per se. So, ocean pH, that means the acid or basic level of the water, can actually vary as well. So, dissolving minerals generally makes the water more basic, or what we call alkaline in chemistry. But increasing CO2 absorption makes the water more acidic. So, as we increase CO2 levels in our atmosphere, it actually acidifies our ocean and makes it more acidic than what ocean creatures are used to. And that again is because the ocean is a carbon dioxide sink. It actually will make like a carbonic acid, like a very light acid. So the properties of seawater, it can have various densities. As it has more salt in it, it gets heavier and it sinks. And remember, cold water has more salt. So cold water has more salt, it gets heavier, it will sink to the bottom. Cold water doesn't, and salty water, I'm sorry, salty water does not freeze as fast. So while regular water will freeze at 0, salty water won't freeze until -2. So it can get a lot colder when there's a lot of salt in the water. And light absorption changes with depth. This is really interesting. I've been diving down deep where the red has disappeared about 65 feet. And I was going through lava tubes and I scraped all the skin off a current came and scrapes me against some lava rock, and I just lost all the skin off the front of my thigh. And so I immediately started bleeding. And I looked down at my leg, and the coolest thing, and I wish I would have taken a picture, I was totally bleeding green. It was the coolest thing. I didn't even care that my thigh got scraped. I almost wish that I'd have an accident and it happens again like that, because it didn't scar or anything, but it made the coolest green blood come out of my leg instead of red because you can't see red this deep. So it looked like I was some kind of witch or something, bleeding green underneath the water. And everybody that was diving with me just wanted to stare at my leg, and we all did. It was just really cool. So goofy stories there of divers. But anyways, so in the water there are different temperatures, and I believe one of the questions in the back of the chapter asks you about this. About 0 to 100 meters is the surface layer temperature of water. Underneath that, 100 to 1,000 is a thermocline. That's like a transition, but you literally can feel when you go through the thermocline, you can feel there's a sudden temperature difference, and you can go up a couple feet, totally warm, down a couple feet, freezing cold. And then underneath that, a bottom layer, 1,000 to 4,000 feet. I have never been that deep. That would likely crush a human, I'm guessing. So there's no, in the polar regions, they do not have this. It tends to be one solid temperature in the polar regions. And I want to talk about how um, salt water is made. It tends to be very, very nutrient rich, but as this ice in the polar region forms, it doesn't make salty ice. It is, the ice is fresh water. So it leaves the salt behind. So there's less water compared to the amount of salt, which makes it saltier. That water gets extremely heavy and it's cold. So it falls down, and it falls down underneath and starts slowly moving in these underwater currents. And it actually takes, it also like gathers, as it moves in these underwater currents, it gathers a ton of things that have died over time, which are high in nutrients. And so this is very cold, almost freezing, dense water that is slow moving and gathering so many nutrients. And this water actually, because it's so slow moving, will actually take hundreds. That sounds like an exaggeration, but it's not. It takes hundreds of years for that water to move to warmer areas of the planet. That's how slow moving it is. But in California, we are, I guess, gifted, blessed with this really cold upwelling of very nutrient dense but extremely cold and extremely salty water. And it comes up in our area, and it makes our oceans, although it's very cold, it's very nutrient rich. So we have a very lively ocean on our coasts. But we do have colder water than other places, but that water that you can feel upwelling from the bottom has been traveling for hundreds of years from the poles to reach you and freeze you on your summer vacation to the beach. So that's what I wanted to go over in this section. Good luck, and I hope you have fun studying our oceans.